Welcome back to Hands-on Machine Learning with PyTorch. So far in the series, we've covered the foundations of machine learning, starting with linear regression using a single feature, then moved on to multi-feature regression, followed by binary and multi-class classification using real-world datasets. In this tutorial, we're stepping up into the exciting domain of computer vision by working on the famous MNIST handwritten digit classification problem. We'll be building a convolutional neural network from scratch using PyTorch, a model architecture that's incredibly effective for image data. Along the way, we'll explore the dataset visually, pre-process the images, define the CNN architecture, train the model, evaluate it at its accuracy, and finally test it on new handwritten digits. So if you're ready to take your deep learning skills to the next level, let's dive into building our first image classifier using PyTorch. In this tutorial, we are diving into handwritten digit classification using the MNIST dataset with PyTorch. Before anything else, we begin by importing all the necessary libraries: Torch and torch.nn for building and training neural networks, torchvision.datasets for loading the MNIST dataset directly, torch.utils.data.dataloader to efficiently batch and shuffle data, matplotlib and seaborn for plotting and visualization, and finally sklearn.metrics for evaluating our model's performance with tools like confusion matrix and classification report. Next, let's talk about transforms. So when working with image data, especially in PyTorch, it's common practice to define our transform pipeline. This is a sequence of operations applied to each image before it's fed to the model. Here, we use two important transforms. The first one is transforms.toTensor. This converts an image from a PIL format to a NumPy array into a PyTorch tensor, and also scales the pixel value from the range 0 to 255 to a normalized range 0 to 1. This is important because tensors are what PyTorch model understands. The second step standardizes the image by subtracting the dataset's mean 0.1307 and dividing by the standard deviation 0.3081. So this helps the training process converge faster by keeping the data in a stable range. The mean and the standard deviation is calculated by some researcher on this particular dataset because it is a widely used dataset. Then we move on to loading the MNIST data itself. We call dataset.mnist twice, once with train equal to true and once with train equal to false. When train equal to true, it loads the 60,000 training images. These are the images that the model will learn from. When train equals to false, it loads the 10,000 test images. These are never seen by the model during training and are only used to evaluate how well the model performs on unseen data. We also pass in the transform to ensure every image goes through the pre-processing steps we just defined, and download equal to true ensures that the dataset will be automatically downloaded for the first time we run this script. This setup prepares us with clean, well-formatted data that's ready for training our deep learning model. Now that we have the MNIST dataset downloaded and transformed, it's time to prepare it for training using PyTorch's dataloader. So what exactly is the dataloader? In PyTorch, a dataloader is a powerful utility that helps in efficiently loading data in batches, shuffling data, and handling parallelism with multiprocessing, all of which are crucial for training machine learning models more effectively. We create two dataloader objects here. Train loader is for the training dataset. We set the batch size to 64, which means the model will process 64 images at once. Before updating the weights, we also set shuffle equals to true, which ensures that the model sees the data in a different order each epoch. This randomness helps prevent the model from overfitting or learning the order of the data. And then the test loader is used to load the testing dataset. We set a larger batch size of 1000 since we won't be updating the model during evaluation. We also turn off shuffling by setting shuffle equal to false because we don't need to randomize the order during testing. Now, before we jump into building the model, it's a good practice to perform some exploratory data analysis, EDA. In our case, just a visual inspection of the dataset. So we define a small function, show_samples, that displays the first 20 images from the training set along with their actual digit labels. This helps us understand what kind of data we're looking at or working with. We are using matplotlib to visualize the grayscale images, and each subplot includes a label for reference. As you can see in the output here, the digits are handwritten, very slightly in difference in thickness and style, but are clearly recognizable. This confirms that the dataset is well structured and ready for training. Now, with the data inspected and loaders ready, our next step is to build the neural network model that will learn to classify these digits accurately. But before jumping into building the neural network model, let's take a moment to do one more quick exploratory check. Something that's often overlooked but extremely important, the class distribution. We're going to analyze how the digits classes are distributed in the training set. Are some digits underrepresented? Are others more frequent? This information helps us ensure that our dataset is balanced, because a model trained on imbalanced dataset can become biased towards the measured T classes. So to do this, we extract the labels from the training dataset and use Seaborn's count plot to visualize how many samples exist for each digit class from 0 to 9. As you can see in the resulting bar chart, the distribution is fairly uniform, with each digit class having approximately the same number of values, around 6,000 each. This is a great news because it means our model won't need special handling like oversampling or class weighting to deal with imbalance. With that final bit of EDA now complete, we're now ready to move on and build our neural network to classify handwritten digits from the MNIST datasets. Let's now define our convolutional neural network model using PyTorch. We begin by creating a class called CNN model, which inherits from nn.module. This is the base class for all neural networks model in PyTorch. In the constructor, we define the architecture of our CNN step by step. The first layer is a convolutional layer defined as conv1. This layer takes in the grayscale image with one input channel and applies 16 different filters, each of size 3 times 3. We've added padding to ensure that the output size remains the same as the input. This layer's job is to detect low-level features in the images like edges, the building blocks of visual understanding. Next, we introduce a max pooling layer. Pooling doesn't learn parameters like convolution does, but instead it reduces the spatial size of the feature maps. In our case, we apply 2 by 2 pooling, which halves the height and width of the input. This helps reduce computational cost and makes the model more robust to small translations in the image. We then add second convolutional layer con2, which takes 16 output channels from the previous layer and applies 32 new filters. This layer allows the network to learn more complex pattern. Think of it like combining simple edges into shapes. Again, we follow it up with another max pooling operation to further reduce the spatial size. At this point, our original 28 by 28 image has been compressed to 32 feature maps of size 7 by 7, a compact and meaningful representation. Now that we've extracted rich features from the image, it's time to interpret them. So we flatten the feature map and pass them through a fully connected layer with 128 neurons. This dense layer acts like a decision-making unit, interpreting the features and figuring out which digit they most likely represent. Finally, we have our output layer, a fully connected layer with 10 neurons, one for each digit from 0 to 9. This layer outputs raw scores for each class known as logits. These logits will later be converted into probabilities when we compute the loss using cross-entropy, which handles softmax internally. So this architecture gives us a compact but powerful model that's well suited for image classification tasks like MNIST. It combines the strengths of convolution for spatial understanding with dense layers for final decision making. Now that our model is defined, it's time to specify how it learns, and for that we need two key components, the loss function and the optimizer. We begin with the loss function, and in this case we're again using the cross-entropy loss. This is the go-to choice for multi-class classification problems like MNIST, where we have 10 possible digit classes. Here's how it works. The model outputs raw scores called logits, not probabilities. Cross-entropy loss then takes those logits and internally applies a softmax function to convert them into the probabilities. It then compares those predicted probabilities with the actual target levels and computes the error. The higher the error, the more the model needs to adjust. Next, we define our optimizer and we're using ADAM, short for Adaptive Moment Estimation. ADAM is one of the most popular optimizers in deep learning because it combines the best of two techniques, momentum and RMS prop. It adjusts the learning rate for each parameter individually, making it faster and more efficient during training. We've set the learning rate to 0.001, which is a common starting point. This learning rate determines how big a step the optimizer takes while updating weights in each iteration. So together, the loss function and optimizer form the learning engine of our model. One evaluates how wrong the model is, and the other helps fix it in the right direction. Now let's move on to the most important phase, training the model. We define the number of epochs, which is the number of times the model will go through the entire training dataset. Here we've set it to 5, which is good for a quick demonstration, though we typically train for more epochs for better performance. Now inside the training loop, we start by setting the model to training mode using model.train. This ensures that certain layers like dropout and batch normalization, if present, behave appropriately during training. Next, we loop through our data using train loader. Remember, the data loader provides batches of images and labels. This makes training faster and more efficient by processing multiple samples in parallel. For each batch, we first call optimizer.zeroGrad to reset the gradients from the previous step. Then we make predictions by passing the images through the model. We calculate the loss using the criterion we defined earlier. We then call loss.backward to compute the gradients, and that is where PyTorch's automatic differentiation engine kicks in. And finally, we use optimizer.step that updates the model weights using those gradients. We keep track of the loss during each batch and compute the average loss at the end of the epoch. So this will help us monitor how the model is improving over time. And after each epoch, we print out the loss so that we can see the training progress live as it happens. Now that we've completed the training process, let's take a moment to visualize how well our model learned during training. We plot the training loss we recorded at the end of each epoch. The x-axis represents the number of epochs and the y-axis shows the average loss for that particular epoch. So as we saw earlier, a downward trend in this curve indicates that the model is learning. It's minimizing the error between its predictions and actual labels. So ideally, the loss should decrease smoothly over time. If the loss is not decreasing or fluctuating wildly, it could indicate issues like a learning rate that is too high, or maybe insufficient training data, or maybe an overly complex model. So this simple plot gives us a quick and powerful way to assess the effectiveness of our training process. Now that the training is complete, it's time to evaluate how well our CNN model performs on unseen data, in this case, the MNIST test set. We begin by setting the model to evaluation mode using model.eval. This is important because certain layers like dropout or batch normalization behave differently during evaluation as compared to training. Next, we loop through the test data set using the test data loader. We use torch.nograd to prevent PyTorch from tracking gradients, which improves efficiency during inference. Now, for each batch of images, the model predicts the class probabilities. We then use torch.max to extract the predicted class with the highest score for each image. We collect all predicted labels and true labels so we can assess the model's overall performance. Finally, we print the classification report. This includes precision, indicating how many of the predicted digits were correct, recall, how well the model identified all instances of each digits, the F1 score, which shows the harmonic mean of precision and recall, and an overall accuracy across all 10-digit classes. So this gives us a comprehensive picture of the model's performance, showing not just whether it got answers right, but how confident and consistent it was for each class. To gain even more insight into our CNN model performance, let's take a look at the confusion matrix. So the confusion matrix gives us a detailed breakdown of the model's prediction compared to the actual labels. On the heat map, the rows represents the actual digit classes, the columns represent the predicted classes, and each cell shows the number of times a digit from one class was classified as another. So ideally, we want to see a high values along the diagonal, which indicates the correct predictions, Any non-zero values of the diagonal represent misclassification, places where the model got confused. For example, if the number 5 is frequently mistaken for a 3, you'll see a noticeable value in the row for actual 5 and column for predicted 3. So by analyzing this matrix, we can identify which digits are causing the most confusion and potentially use that insight to improve our model, whether by tuning the architecture, increasing data, or augmenting samples. So this wraps up our evaluation phase. Finally, we will now test our model on a single image to see how it performs in action, just like a real world prediction scenario. We start by picking the first image from our test dataset and showing it using matplotlib. The title above the image shows its true label so that we can later compare it to the model's prediction. Next, we prepare an image for inference. Since our model expects a batch of images, we need to add an extra dimension to convert this single image into a batch of size 1 using unsqueeze. Then we pass this sample through the trained model and get the output logits. By applying torch.argmax, we extract the classes with the highest score that gives us the predicted digit. Finally, we print out the prediction. If the predicted class matches the true label, it's a good indication that our model is on the right track. So this kind of simple test can be useful for quick sanity checks and building interactive applications with real world predictions. If you've reached up to this point in this tutorial, great job making it to this end. So in this video, we built a complete convolutional neural network using PyTorch to classify handwritten digits from the MNIST dataset. We started with data pre-processing and transformations, explored the data visually and understood its class spread. Then we designed a simple but effective CNN architecture, trained the model and tracked the losses over epochs to monitor learning progress. After training, we evaluated the model's performance using a classification report and confusion matrix, which gave us detailed insight into how well our model performs across all digit classes. Finally, we tested it on a single sample to simulate a real-world prediction. This project brought together key elements of deep learning: data handling, model building, training, evaluation, and inference, all in one pipeline. So in the next video, we'll take things a step further. We'll explore how to save and load models, making your trained model reusable for future applications. So don't forget to like, subscribe, and drop a comment if you learned something new, and I'll see you in the next tutorial.